Hello, everyone. So in this session, we'll be doing coding for convolutional neural network. Okay, let's start. So as an intro, a convolutional neural network, or CNN, is a type of neural network where at least one layer is a convolutional layer. A typical CNN architecture brings together the following. So you have a convolutional layers to detect features, pooling layers to reduce spatial size, and dense layers for decision making. So that's really your final layer for the output. And CNNs excel in image recognition, where they've set new benchmarks. Although more recently, transformers can also do the same task, but for the longest time, it's always CNN. It's the de facto neural network architecture that you're going to be using for pretty much anything that has to do with images and videos. Okay, so I've mentioned earlier convolutional layers. So what's convolution? What is a convolutional operation? So a convolutional operation is a two-step process that applies a filter over a slice of the input matrix. So example, you have this element-wise multiplication layer between the filter and the matching section of the input matrix, and then summation of all the values in the resulting product matrix. So let's consider the following example. We have a 5 by 5 input matrix here. See 1 to 8, 97, and etc. Now consider that you have the following 2 by 2 convolutional filter. What happens is this. So a convolutional operation would slice the filter over the different parts of the input matrix, creating a new matrix that captures the patterns from the original data. In this example below, the convolution is applied to the top left 2 by 2 input slice. So again, this is the original 5 by 5 input matrix. You get the top left here as an example, and then you simply do um, an element-wise multiplication here, and then you just sum it all up, right? So you get 1 to 80022 because your convolutional filter is 1001. So it's just this, and then you just add them all up, and then you end up with 150. So that's gonna be your value now. It's just one cell. And you keep on doing that for all of the slices. So you keep on just sliding here. So the next one will be this, right? And then this one, and then this one, and you keep on doing that for all of the rows as well. So you end up with a new matrix now. So let's start implementing that in Python. So as usual, here are some preliminary imports that I usually do with all of my notebooks. And we're going to be using TensorFlow and Keras API for this one. So you just import it. For this notebook, we'll be making use of the Sephartan dataset. It consists of 60,000 colored images across 10 classes, 6,000 images per class. It's already split into 50K training images and 10K testing images with no overlap between the classes. So this is how you do it. And we've also done some normalization because it's 0255. It's generally the values that you have for colors. But we're normalizing it to make it 0 to 1. If you check the shape, it um, is consistent with what I've said earlier. Now let's do some verification of the data. So here are the 10 classes that you have in Safari 10 dataset, right? So here are the class names, and we're just, gonna show them just for you to understand the data better. So this is 32 by 32. Okay. Okay, so now let's start to do the modeling. So let's build the convolutional base. The convolutional base of our model will be a stack of conv2D and max pooling 2D layers. These layers will process input tensors of shape, image height, width, and the RGB color channels. For Sapphire, that's 32 by 32, so that's the height and width, and then the three color channels, RGB. Each conv2D and max pulling to these layers output is a 3D tensor, height width channels, with height width shrinking progressively. Remember the convolution operation, right? If you keep on doing that, it will make your matrix smaller. So as you add more layers, it will become smaller and smaller, and then you have lots of features. And as you go deeper, you generally increase the features so that it can capture the finer details in your dataset, even as we reduce the spatial dimensions. So this is the code for that. So you can see the conv2D layer here and the max pooling 2D. And the activation that I use is ReLU or rectifying um, leak leakage unit, if I remember it correctly. And then the input shape is 3232 by 3. You have to specify that, and then you just keep on stacking them. So we use 32, 64, 64. These are arbitrary values, but generally the rule of thumb when we're doing this is that we use numbers that are powers of 2. So like 2, 4, 8, 16, 32, 64, 1 to 8, and you get idea. Oh, sorry, I remember now. It's rectifying linear unit, right? Yeah. The leaking part is for Likirelu. I sort of remember that while I was saying that. So it's rectifying linear unit. There's Likirelu, which is another activation function which incorporates the leakage component there. So that's why it's called Likirelu. My bad. Okay, now that we have built the convolutional model now, um, we're gonna add dense layers on top of it. So we do that to make the final predictions. And generally, the last uh, layer that you have corresponds to the output classes that you have. So in this case, it should end with the 10 because we have 10 classes. But you can add lots of dense layers along the way. But the final should be 10, which is the number of classes that we have for this data set. So we're gonna take the output from the convolutional base. The shape is 4 by 4 by 64. If you check the model summary here, you're seeing that. And we flatten it into a 1D vector. That's the first thing that you're seeing here. You flatten it, and then after that, you add the dense layers. And it should end with 10, as I mentioned. And then after that, you just compile it. You could also pay more attention to the number of trainable parameters here. That's generally the size of the model. If you hear about like, a billion parameter model, that's it. That's what you're seeing here. So it's a relatively lightweight model, only about 90K parameters. Okay, now we're compiling it. We use Adam Optimizer and then categorical cross entropy. And then we track the accuracy metric. And then you just plug in the data set here. And we're going to have 5 epochs. So now you're seeing the accuracies for the different epochs. So we end up with about 70-ish accuracy for both train and test set, which is good. With such a straightforward architecture, few layers, with minimal tweaking, we already got 70% for this data set. If you want to see the plot, it's this. And that's it for the CNN coding notebook.